In the case of a metallic conductor, does heat conduction spread quickly due to the thermal kinetic energy of atoms? Or is it transmitted through electrons inside the conductor? In the case of metallic elements, thermal conduction is rapidly propagated by the kinetic energy of electrons. Metals consist of atoms arranged in a crystal lattice, with free electrons able to move freely between these atoms. When one end of a heated metal is energized, the free electrons gain thermal energy and their kinetic energy increases. These free electrons transfer their kinetic energy by colliding with the surrounding atoms, and this process repeats, allowing heat to propagate to the opposite end of the conductor. On the other hand, thermal conduction, due to the thermal motion energy of individual atoms, is very slow. This is because thermal energy of atoms is transferred through collisions between atoms. This process is much slower compared to thermal conduction by free electrons. So it can be said that heat conduction in metals is primarily driven by free electrons. In practice, the thermal conductivity of a metal is proportional to the density of free electrons within the conductor and the mobility of these free electrons. This means that metals with a high density of free electrons and fast electron mobility have higher thermal conductivity. For example, silver is known to have the highest thermal conductivity among metals due to its high density of free electrons and fast electron mobility. In contrast, lead has a low density of free electrons and slow electron mobility, making it the metal with the lowest thermal conductivity. So when semiconductors such as silicon or germanium are heated, does the movement of free electrons become active and current flow freely? Semiconductors like silicon and germanium become conductive when heated, allowing electric current to flow more freely. Pure semiconductors consist of atoms arranged in a crystal lattice with very few free electrons between them. However, as the temperature rises, the collisions between atoms and free electrons increase, leading to an increase in the number of free electrons. Additionally, the kinetic energy of free electrons increases, resulting in longer electron mean free paths. As a result of these effects, heated semiconductors allow electric current to flow more freely. However, the electrical conductivity of semiconductors is much lower than that of metals. This is because the density of free electrons in semiconductors is low, and their mobility is slower compared to metals. In reality, for example, in the case of silicon, with a purity of 99.99% at a temperature of 300 K, the density of free electrons is approximately 10^16 semi-3. This is a significantly lower value compared to the density of free electrons in metals. Additionally, the mobility of free electrons in silicon is about 1/100th that of metals. To increase the electrical conductivity of semiconductors, methods such as doping with impurities to increase the number of free electrons or enhancing the mobility of free electrons are employed. So, in the case of a permanent magnet with a constant spin direction, if thermal kinetic energy is applied, will the spin direction become inconsistent and the magnetism disappear? The magnetism of permanent magnets arises from the alignment of atomic spins in a consistent direction. When thermal energy is applied, the kinetic energy of atoms increases, disrupting the ability of atoms to maintain their spin alignment. As a result, the spin directions become inconsistent, leading to the loss of magnetism. The magnetism of permanent magnets decreases as the temperature rises. This occurs because, with increasing thermal energy, atomic spins can no longer remain consistently aligned. The temperature at which magnetism disappears varies depending on the material of the permanent magnet. For example, iron loses its magnetism at 770 degrees Celsius, and cobalt loses its magnetism at 1130 degrees Celsius. To maintain the magnetism of permanent magnets, it's essential to keep the temperature low and avoid subjecting the magnet to physical shocks. Applying shocks can deform the atomic structure, potentially leading to the loss of magnetism.